Hello everyone, my name is John and I will be presenting my final project with the title Deep Learning Based Visual Odometry for Aerial Visual Positioning Systems. First and foremost, drones often need to operate in GNSS denied environments, that is, environments where GPS can be unreliable or completely unavailable. This includes indoor spaces, places where adverse weather conditions exist, mountainous terrain, and also areas with high electromagnetic interference, also known as jamming. Visual positioning systems are a state-of-the-art alternative that enables navigation using optical sensors, and therefore we can achieve high accuracy and operation in any environment. Visual odometry is a core component of visual positioning systems, and this is the technology that we will going to implement in the context of this project. So, drone navigation involves many sensors, from inertial measurement units, which provide high frequency angular velocity and linear acceleration, but suffer from bias-induced drift, to cameras and lidars. Cameras can be leveraged to acquire drift correcting constraints based on visual environmental features, and lidars produce 3D point clouds, which can be utilized to estimate movement from differences among geometric environmental features. So we have a difference between cameras and lidars in terms of cameras capture RGB images that we all know, and lidars capture 3D point clouds or meshes. Artificial intelligence is employed to find such environmental features from images, but also to make sense of temporal changes in such sequences and estimate and refine ego motion. Ego motion is motion from frame to frame, or rather, ego motion is relative movement and not movement relative to a world frame. So, what exactly is visual odometry? Visual odometry estimates this relative movement or ego motion from image sequences. It assumes that movement of visual features can be translated into movement of camera frame. So if the features move to the left, that means that our camera moved to the right. Visual odometry inherently suffers from drift if no global correction techniques are implemented, because errors accumulate over time. Visual odometry can be generally divided into classical visual odometry and learning-based visual odometry. Let's briefly discuss classical visual odometry to see how learning-based visual odometry is better. First of all, classical visual odometry is based on non-learned descriptor-based pipelines. That means that it involves feature detection, feature matching, and then algorithms like ransack or some other algorithm to achieve pose estimation. A good thing about classical visual odometry is that it is well understood, interpretable, and pretty fast. It is also very efficient on environments that contain a lot of texture. Nevertheless, it is sensitive to motion blur and lighting changes. It struggles with repetitive patterns such as waves in the ocean or a highly repetitive agricultural field. And it also struggles with scale ambiguity in monocular aerial imaging. This is the one that the last struggle of this slide is what makes us choose to implement a learning-based odometry system rather than a classical visual odometry system. So classical visual odometry cannot generalize well with scale, or that well. Learning-based visual odometry, on the other hand, treats odometry as supervised regression. It deploys neural networks, most commonly CNNs, and the complete learning pipeline maps consecutive image pairs to motion vectors. So we get an image pair, the neural network maps it to motion, to movement. The visual features are automatically learned through the CNN, much like the CNNs do in classification tasks or other tasks. Feature matching becomes automatic through the neural network, and this learning-based visual odometry is more tolerant to blur, lighting, and weather variations. Scale invariance can be achieved automatically with enough dataset diversity. So if you have a large and diverse dataset, then our model will be will be efficient in all scales present in this dataset. So, our proposed system focuses exclusively on visual odometry module. We are implementing completely learned visual odometry with a convolutional neural network. We will not implement loop closure, global optimization, or relocalization in the context of this project. We are only designing a component of a fully functional visual positioning system. Nevertheless, our visual odometry module will be totally compatible with future visual inertial fusion, or we could integrate loop closure and global optimization in the future. More on that in the next slides. So, how we selected the dataset, how the dataset was selected. Commonly, ground vehicle visual odometry datasets are not rare, are very common, but they are not suitable for this project. This is because the angles the angles from which images were taken in such datasets are oblique, and they're not easily translatable to motion. There was a need for downward-facing monocular grayscale cameras, and it was actually a requirement for the effectiveness and simplicity of this project. A lot of datasets were also made in simulated environments. However, it was preferred that real drone flights were used. The dataset that was used eventually is the FGI Masala Stereo Visual Inertial dataset, made back in 2021, and it matches all the requirements. It consists of real drone data taken from a downward-facing camera, and it contains accurate odometry for each trajectory. It includes trajectories at 40 meters and 60 meters of altitude, with varying drone speeds for each altitude, from 3 to 4 meters per second. The dataset is provided as ROS bags. ROS is the robotics operating system, and in the beginning I was afraid that it would require installation, but fortunately there is a Python library called ROSBag, and I was able to extract the images from the trajectories along with their timestamps pretty easily with this Python library. There was a problem, however, which was immediately evident. Poses were less in number than image frames, much less in number actually. But the fortunate part is that they spanned the entire trajectory length in time. So the solution was to simply interpolate the poses, and this created a type of approximate synchronization. From each pose to the next, we did interpolation, and we assigned the interpolated poses to the images that were much more in number. We did the linear interpolation for the position and SLERP for the orientation, which is spherical linear interpolation. So, how did we formulate the learning of our neural network? First of all, the two consecutive image frames from our video were stacked, and this stacked two-channel image was the input of our convolutional neural network. Then the input was this two-channel image, and the output was a planar motion vector delta x delta y. So we predicted only xy motion. We left the x-axis out for now because for two reasons. We could incorporate it later, but the dataset contains constant altitude trajectories, so we would have to mix a different dataset to incorporate z movement. Motion was expressed in camera local coordinate frames, so we had to actually make a transformation of our data, because in our dataset the poses were relative to a world coordinate frame. We had to make them into a local coordinate frame, so to turn world motion into ego motion. And If we aggregate these ego motion poses from one image to the next, so from one frame to the next, then we have a trajectory, and this leads to our final output, which is trajectory estimation. So our model architecture, it is simply a compact convolutional neural network with 4 convolutional layers. ReLU activation was used, and batch normalization was employed for speed and stability. I also put in there some global average pooling in the end to reduce overfitting and reduce the dimensionality of my images. And I also initially selected to incorporate a single dropout layer for regularization. The architecture ends with a fully connected regression head, as usual, which outputs the delta x delta y motion vector. The training in the beginning was a bit it was not very high quality. Overfitting was exhibited, and also some instability was also present, and spikes in the validation curves. Nevertheless, the training curve was good, so that indicated that with minor changes, minor adjustments, it would go well. And indeed, after after changing the train validation split to include more phases of the flight, so to be certain that the model is trained on liftoffs and landings, and also in the mean of the trajectory, the median part of the trajectory, already improved the results. I also added an ADAM optimizer with weight decay and an extra dropout layer for even more regularization and less overfitting. Finally, and this was an important upgrade, I incorporated data augmentation and specifically color jitter, blur, and random erasing. This created a much smoother training curve and a much lower validation loss, which was also much more stable. So, some results. The metrics used to evaluate our model was mean per step error, final endpoint error, and cumulative error. The mean per step error is how much error is in each ego motion, and the mean, we take the mean of that. The final endpoint error is the error between the final pose, ground truth pose, and the predicted final ground truth pose. This is actually one of the most important metrics in such odometry experiments. The cumulative error is the ego motion errors added all together. So we can reconstruct the trajectory from ego motion by simply aggregating all ego motions and plotting them, and it is easy to make qualitative assessments as well from the curves that we can see on the right here. The endpoint error was only 30 to 40 meters, and that was for 600 meters and more of flight, even more lengthy flights, so it was acceptable. And we can also see qualitatively that our model generally tries to follow the ground truth trajectory, which is very good. And we also got smooth and locally consistent trajectories, which was what we expected, and it's a very good sign. Some limitations are that drift error will always accumulate without loop closure in such models. Odometry and drift error go together if we don't put some loop closure in the mix. The utilized dataset was high quality indeed, but it lacked diversity and size. It was a dataset taken from a single drone and on a single area. Larger datasets and more variety would be very beneficial for our model. Finally, we should note that CNNs have no temporal memory. They are frame to frame only, and trajectories are sequence data. So why not use a model that is more specialized in sequences? And all this is reflected here in the future work. We could use learning-based loop closure techniques, such as visual autoencoders for place recognition. This would be a natural extension. We could also increase the dataset size and incorporate new datasets, more diversity. We could replace CNNs with the CNN with CNN, LSTM, or transformer models, and we could fuse the visual odometry module with IMU LiDAR module, and this would lead us to an almost complete visual positioning system, which would be a very interesting feature direction. Thank you very much for your attention.